We're now going to define a composite function. The notation that is used is an open circle in between the f and g. And what we say here with this notation is f composed with g of x. Now when we see this notation, what it means is that we're going to take the g function and plug it into the f function. Now let's recall that it's common practice with functional notation to sometimes say f of x, and sometimes we just call a function f, leaving off the of x bit. And when that's left off, of course, it is implied. Similarly, we could say f composed with g of x, or we might just say f composed with g, but both of those notations mean the same thing, that we're going to plug the g function into the f function. Before we look at an example, let's remember what it means to plug something into the independent variable spot of a function. Essentially, we go to the f function and open up a hole for that independent variable, and whatever is indicated inside here is what we plug into that independent variable spot. Let's copy paste the left-hand side and see that on the right we get -3 plus 2, and the function evaluated at -1 in this case turns out to be -1. When we plug a number into a function, what we get out is also going to be a number. But we are not restricted to plugging in numbers. We could plug in variable expressions. But even if it's a variable expression, we do the same thing. We go to the f function, we open up a hole for the independent variable, and whatever is indicated inside the functional notation is what we plug into that hole. Again, let's copy paste the left-hand side and simplify the right-hand side by distributing in the 3. And as a matter of fact, there's nothing else that really can be done. Nothing cancels or combines. So we'll call this done. But notice when we plug a variable expression into a function, what we get out is also a variable expression. Now let's take a look at this functional notation, f composed with g of x. And remember, by definition, what this means is that the g function is going to be plugged into the f function. Essentially, the function that is on the left is going to be the function that's on the outside. So what we'll do here is we will write the outside function with a hole for the independent variable spot, and what goes into the hole is going to be the g function. But instead of writing it like g of x, let's replace that g function with what it actually is, which is 4x. And that's what's going to go into that independent variable spot. Let's copy paste the left-hand side so we don't forget what we are actually finding here. But instead of using this notation, let's use the composite notation, f composed with g, and notice I'm dropping the of x bit to use the shorthand version. So this is a new function, we'll call it f composed with g, and it simplifies on the right to be 12x plus 2. And so now we have 3 functions that we're looking at. One of them is called the f function. Another is called the g function, and we also have the f composed with g function. In part D, notice that what we've changed is who is on the outside. Now, the g function is on the left, which means that is the function on the outside. So we'll write the g function down first, leaving a large hole for the independent variable x. What we plug into that x spot is going to be the f function, but instead of writing it as f at x, we're going to use what f at x actually is, which is 3x plus 2. So 3x plus 2 is what we plug into the independent variable of the g function. And now let's simplify this as much as possible. Again, let's copy paste the left-hand side so we don't lose sight of what it is that we're finding. But instead of calling it g composed with f using that notation, let's use this new notation, g with an open circle, which means g composed with f. Again, we could say g composed with f of x like this, but the shorthand version is just saying g composed with f. Now let's distribute in the 4 to get 12x plus 8, and we can't simplify this anymore, so we'll just box this up and call it now my g composed with f function. Notice we now have 4 functions, the f function, the g function, the f composed with g function, and the g composed with f function. And these all have their unique names. So I've copied down the f composed with g function and the g composed with f function so that we can now, in part E, evaluate f composed with g at -1. So what this means is to go to the function whose name is f composed with g, and of course that's this function here, and then plug -1 into the independent variable spot. So the first thing that we're going to want to do is to copy paste our f composed with g function, which is 12x plus 2, and then we put whatever is indicated inside the functional notation into the independent variable spot of our function. And then we simplify. So 12 times -1 is -12, and then we add 2 to that, and we copy paste the left-hand side with every step so we don't lose sight of what it is that we're calculating. So f composed with g of -1 turns out to be -10. Now let's evaluate the exact same quantity but using an alternate method. And the alternate method that we're going to use is the definition of the composite function. By definition, when we see f composed with g like this, what it means is that we're going to take the g function and plug it into the f function. But what we're going to be using in the independent variable spot this time is -1. And again, this is the definition of what this f composed with g notation actually means. So basically we have a function within a function, and let's go to the very inside to determine what g evaluated at -1 actually is. Remember, the g function is 4x, so g evaluated at -1 means to go to the g function, open up a hole for the independent variable, and plug in whatever it is that we see inside this functional notation. So g evaluated at -1 is -4. Now, since g at -1 is -4, that means that these two quantities are interchangeable. So f evaluated at g of -1 is the same thing as f evaluated at -4, replacing g at -1 with -4. So now we see f at -4, which also has meaning to us. What that means is to go to the function whose name is f. Write that function down, leaving a hole for the independent variable. And then whatever is indicated inside the functional notation is the quantity that goes into the hole. So again, we have -12 plus 2, which is -10. And remember, what we started with on the left-hand side was f composed with g evaluated at -1, and what we landed on was an output of -10. That's the same output that we got a moment ago. So in summary, we can evaluate a composite function at some domain element by either finding the composite function and then plugging the domain element into it, or by using the definition of the composite function, evaluating the inside function at that domain element, plugging that result into the outside function, and then finally evaluating the overall result.